Okay, so we use the transfer function to we can model the circuit, the system using transfer function, and also we can also model the circuit, and then we learn about the time domain, which is the state space. All right. So now we are ready to move to the second part. Okay. So for the second part is we are learning about how to analyze the. We're going to learn some tools on how to analyze the system. Okay. So for example, we are given the transfer function that represents a system. Okay, so we're going to identify what type of system is that. Is it a system type? Is it a system first order or second order? And also from there, we analyze the step response. Okay, so what are the specifications that we need to know for the step response? So that one will become in this part. Okay, and it's just that we talk about, I told you that whatever you do in your part 1, you have to the denominator has to be equal to 2. Why? So that is what we cover here. So, okay. So the content, there are five things that we're going to cover for this time. Okay. So the first is on the transfer function. Okay. What is transfer function and how do we do the zero and poles for the transfer function? Okay. And then secondly, we're going to cover here we're going to expose to first order system, and then second order system, and then the general second order system, and what are the specifications for the unknown second order system. Okay. So, okay, I closed my video actually. My video. Okay. So transfer function. Okay. For this one, we have the transfer. We already talked about. You look at A. So for example, we have a system that is modeled. For example, we have a system that is modeled by a transfer function which is s plus 2 and s plus over s plus 5. So GS here is the transfer function. Okay, and we have the input to the system, which is in this case, it is a step. It's a step input going to the system. So we need to see how is we can predict what is the output response here. Okay, so for this one, you see that the round here is zeros. Okay, and what is this that? Apa ni? This one is poles. Okay, so what is in a transfer function, the denominator here is where we have the poles located, and numerator here is the zeros. So in the steps, in the S domain plane, so it will be, you see that the zeros here, we can plot the zeros here and we can plot the poles here. So it has some meanings to it. We will go through in the advanced chapter. So before that, what we see in this second graph is 1 over S, which is the input, okay, to the pole, okay, and then also here the system zeros, S plus 2, and also the system poles here, which is 1 over S plus 5. So the output that you get mathematically, we know that the transfer function output CS will be equal to the system and multiplied by the input. So in this case, our input is step input. So to expect what the kind of signal that we're going to expect to have is the output that will contain a force response and a natural response. So where we can solve this one. Okay, so it will be S plus 2 over S plus 5 divided 1 over S multiplied by over S, and we use the partial fraction equations to find the 1 over S. Alright, next. So what is this? So this one is the okay. So what we can say is that what we're going to get here is over 5 K1 plus B K exponential e minus 1, 2. So, right? So this is the thing that we are, the post location here will depends on the post generates at the response of key k minus exponential to the power of minus 80. Alright. So let's move on. Okay, so here. So evaluating the response using poles. Okay. So if you look at this one, this system. Okay. So this is a transfer function. Sorry. This is the transfer function. Okay. So the transfer function we know we can see that poles at -2 or -5 and zeros at -3. Okay, so the input to the transfer function is input. So the output to the transfer function is the step input multiplied by the system multiplied by RS. So this is the output of the transfer function. So we it is combined. It will produce a combination of a force response. One of them is due to input. The temperature response. Here is due to the behavior. So you can see S plus 2, S plus 4, and S plus 5. Okay. So this is the S domain. Okay. Domain ini nak transform in the domain. This is what we will get. The force response, the initial response is K2, K3, and K4. Okay. So I will discuss about the maths here. We have covered it in part 1. Okay, let's move. Okay, now first of the system. The general block of the system is the transfer function here. Okay, so as you can see here, the transfer function for the system is, I'm just rewriting it again.
Kami tak dengar.
A over siapa tu bantu tu. A over. Okay. So what is the in the S plane? The A here will be, so in a first order system you only have zeros, which is at minus A. Okay. So in S plane, so in mathematically this is how we get the output response transfer function. And when you transform it into a time domain, it will consist of force response, initial response. So it will be 1 minus exponential minus A2. So the A here is the okay. So okay. What do you need more? Okay, the things that you need to know for a first order system is the time constant. Constant. So the performance that we evaluate for a first order system is the time constant. The time your system to respond from 0 to 63% of the final value. So you see here, this is the value. So I put FV. Okay. Time for the system, which is output here, to respond up to 60% of the value. This is the time that we get here, called a time constant. So mathematically, it is 1 equals to 8. So that means that the time constant is equals to 1 over 8. Alright. So from the time constants, okay, when we know the time constants of the system, then we are able to find the TR. TR is the time for the system to go from 0 for the system to 0, 1 to 90% is the final value. So in mathematics, 2.2 divided by A, which is divided by time constant. And you're also able to know the time TS. So TS is the time for the output to reach to its desired, to it reach to its final value. So mathematically, so we need to discuss what and why it to contribute. So at the moment we just accept it. Okay, that's the first one. Okay, let's take some example. Okay, so remember that masa during the class I told you I like to give at our building so we have 4 elevators. For example, that you are to better press the desired level and then we have the example equals. So we enter the elevator desired level, so we accelerator moving from level so that is okay, which is a start input moving from 0 to not okay, sorry. The elevator moving in, and then the output response of the elevator CS. So if you're talking about one elevator is quite hard to appreciate, but we are comparing the performance of 4 elevators. As I told you, I love the elevator that is to the left side of me. No, sorry, to the right side of me. Okay, the left side is a little bit sluggish. Okay, so the right side is a bit faster. Elevator is one good example of first order system. Okay, so first order system means that, for example, I use the elevator to the left, then it gives me a very sluggish response. It goes to level 7, but a little bit slower. If I use another way, it might go nice, faster, and reach the desired level. Okay, so this is one example of first order system. So from here you can find actually you're able to put the elevator response, you are able to find the response settling time. Okay, so you know the time constant. Time constant. This is the time the elevator to reach 60% final value. The asset is now. Okay, so in the case elevators, probably the time constant this one is level 7. So 60% will be here. If you map it here, I use the black color, the black line here, okay? So you put it down, you bring it down, so you will get the value here, which is 1 over 8. So this is time constant. Okay? So from that time constant, kita boleh tengok balik from the time constant 1 over A, then we get TR 2.2 over A. So our TR is 2.2 over A and TS is 4 over A. That's easy. Okay, that's all for a first order system. So by now, when you're talking about elevator, there are we can assume that the elevator is a first order system. So the performance specification that we are talking about is the rise time and settling time. The time it takes to rise and the time it takes to settle. Okay, so let's move to second order system. Okay. So, okay, this one is the estimating the transfer function. Okay, so this one is one of skill assessment. Okay, so example, I forgot to tell you that example in this case is in our actual system, for example, elevator, if I tell you to model the elevator, okay, so if I told you to model the elevator, it would be impossible because everything is in a box. So it's in the elevator system is one example of black box. You don't know what's inside, we open it up and look at the circuitry inside, it's quite impossible. So another way to model the system is we can measure the output response. For example, the output response of the elevator, for example, is a so it means that the position of the elevator from 0 to level 7 to the level we want. So from this output response, when we have this output response, we can use the theoretical knowledge of time constant, TR and TS to plot the 63% and get the time constant, and we are able to find TR NTS. So from NTS, actually able to build function. I'm going to move back and forth. Okay. So that one which is, sorry about that. So you know that the time constant is A. Okay. So from here, we are able to find the transfer function as here. A over S plus A. Okay. So let's look at example. Okay, this one is a good example. Example that we have one graph of a response from a system. Okay, so we have a system. So it has an input. So definitely it is a start input, and it will produce an output here, which is CS. So this one example, this is a CS. CT. Okay, remember it is CT. Okay, so it shows here that for example, this one is the 63% value.
Sorry, keluar.
This is the 63%. Mana pula?
Yes, ma'am.
Apa dia? Okay, so you guys can see me. Okay, so this is the am I recording or not? Okay, so this is the 63% of the final value, for example, okay? Before you. Okay, so for example, this one is the 63% of the final value, which is the value is 0.0244 seconds. Okay, so so you can actually find the transfer function. We assume that this is first order system. We assume first. So you know that generally the first order system is A over S plus A. Okay, so you know that A is the time constant. One is the time constant, which is the time for the output response. For the output response here to reach 63% of the value. Okay. So example, in this case, the time constant A is 0.0244 seconds. So you just substitute it into here. So it will be GS equals to 0.0244 over S plus 0.0244. Then you get the order in transfer function. Okay? So that's a simple example of first order system. Alright. So can I move on?
Yes.
Okay, all right. So let's move to something a little bit trickier. So this is the fun part of control engineering actually, okay? The second order system. All right, so for second order system, look at up here. This is the general form of second order system. Okay, so I just rewrite it here to B over S squared plus AS plus B. Okay. So, in second order system, there are four kinds of response that you should expect. Okay, so the first one is there are four kinds of response. The first one is the overdamped response. We look at this one first, the graph first. Okay, so the first one is the overdamped response. Okay, so how you can get this response? You look at the transfer function. Here, you look at there are two poles. Okay, so when we factorize this transfer function, you're going to get two poles at the real part, okay, at the real part of the S plane here. So this one, if you get this kind of transfer function, you know that it is an overdam. You can expect to have an overdam output response. Okay, the next one is underdam. Okay, so this is underdam output response. Okay, so you remember, if you can remember that, okay, nanti dulu, underdam. Okay, if you remember that the antenna position control system that I discussed with you in the case study, alright, so if you want to move the antenna to one desired position, okay, so, and we have this kind of response where the antenna moves and it's overshoot first before it reach to the desired position. So if you remember that, okay, so that one is example of, so the response of the dish antenna dish. So if it is, it has some overshoot to another degree and then back to, that's underdamped, okay? But okay, that's quite lengthy. So the third one is undamped, undamped system. So what happens if it's undamped system? In terms of the output response, it will have an oscillatory. Okay, so imagine antenna position, antenna azimuth position control system. If the antenna dish is in oscillatory motion, is that good? What do you think? All right, so that is something that we not desire. So if it is oscillatory motion, so you can imagine that an antenna is moving, swinging, it's like a pendulum, swinging. So if it's talking about a big antenna, so you are talking about safety, you are talking about cost, you are talking about, it affects so many things, safety and cost, especially case safety of human. Okay, so that is example of undamped system. So in terms of S plane, the roots of the undamped system is at the imaginary line. See that? Okay, so the last one is critically damped system. So in critically damped system, you're going to have an output response that is very, 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 very nice here. See that? Okay, so if you have this the transfer function in this form, and when you factorize the denominator, you get two poles at the exactly the same value. So when you plot it as domain, you will get like this. So you can expect that the output response will be critically damped. So that's how it goes. Okay, so I'm going to repeat. If you have a system in this transfer function, for example, overdamp, let's look again at overdamp. When you factorize the denominator here, and you get the value of S, oops, and you get the value of S at the real part, which means that S, when you factorize, you get the value of S at two real values. So when you plot it at the S plane, you get it plot like this, really at the real values. So you can expect that this is an overdamped system. So this is what this whole tables is telling you. Okay. Similarly, if you have an underdamped system, when you have a system that the denominator, when you factorize the denominator, you get a complex poles here. Okay, so you can expect, you can predict that the output response will be an underdamped. Okay, so that's the same goes to the undamped. So when you have the poles, for the transfer function, when you have the poles located, when you get the poles and the poles are all imaginary, when you plot it as plane, it is located at the imaginary line. Now you can expect, oh, this is not nice. This is a marginally stable system. If it's wrongly tuned, it can go to unstable. All right. So there are four types of, in the second order systems. What is it, second order? Okay, look at generally the general block diagram. You have S to the power of 2 here. See that? So it is a second order system. So that goes back to one of the questions of my students. They asked when we are working on the mathematical model. I told you to keep the model as much as possible in such a way that the denominator here is S to the power of 2 plus something, or S to the power of 3 plus something. And someone asked me why do I have to keep this? instead of having some constants here. Why? Okay, so this is the reason. Okay, because we're going to make the system close enough to the general form here so that we can know, we can predict the type of system, either it is overdamped, underdamped, undamped, or critically damped. Alright, so these are the step responses for the second order system damping cases. So you have undamped here, undamped, which is oscillatory. So this is the one that we not desire. Okay, so underdamped system, critically damped, and overdamped. So there are no response you're going to expect for second order system. Okay, so this is the second order step response components generated by complex poles. So whenever we have the exponential minus AT in our signal, okay, we're going to expect that it is something, a signal that is decaying here. There is a natural element that is decaying here. Okay, so that's what is explained here. You can refer to the textbooks to understand more. Okay. Any questions? Okay, let's look at this one. Okay, so write the form of the step response for the system for this one. Okay, so you know that the transfer function here is equals to 200 over s squared plus 10s plus 200. So we factorize this one. The denominator, it will be s plus 20, s plus 10. Okay. So what we're going to expect here, we're going to expect that, remember that the numerator here is the zeros. The denominator here is the poles. So when you plug the poles, you're going to expect that you're going to have, when you plug the poles in the S-plane, you're going to have two poles, minus 10 and minus 20. Okay. So look at the table. For two poles at the real part, what you're going to get? You're going to expect that this is an overdamped response here. So you know that here, so you can expect that this is overdamped response.
Hanya temankan sepi.
Amboi. Okay, so here overdamped response. So what is that overdamped response? So here, okay. Overdamped response. So the response here will be C T to the time. So we look back at the table here. So it is going to be like this overdamped response. So we're going to expect that it's going to be an overdamped response. Okay. So there are more examples that you can see on that. Okay. So let me check first if I'm correct. Okay, so let's move to what you need to know about this underdamped system. What you need to know. Okay, so the general second order, for the second order system, there are two parameters that you need to take care of, right? So the first one is the natural frequency, and the second one is the damping ratio. So what is natural frequency? Natural frequency is the frequency of oscillation of the system without damping, and damping ratio is the exponential decay frequency of the envelope to the natural frequency. So damping ratio is, there is a formula to it, which is the damping ratio. Look at the symbol, okay? Observe the symbol. Okay? So the damping ratio is equals to exponential decay frequency over natural frequency. Okay, so generally the second order system can be formed into natural frequency and damping ratio through this equation. So it's actually, if you look back just now, it will, the second order system is equals to D over apa tadi?
S square AS.
Yes, thank you. S squared AS plus B, right? S squared plus AS plus B. Okay. But if you talk in terms of natural frequency and damping ratio, the second order system is in this form. Okay. So next. Okay. So let's go to some exercise. Okay. Find the natural frequency and the damping ratio of the following transfer function. So again, we look at here. Okay, so the general, you know that this is a second order system. Why? Because this one is S to the power of 2. Okay, so we know that the general form is GS equals to frequency over S squared plus
natural frequency to the power of square.
Damping ratio, natural frequency S plus, I remember, okay.
Natural frequency.
Squared. Okay. So from here, we just can find, okay,
Ma'am,
natural frequency, yes.
Your top also got square. The natural frequency.
Okay, thank you, teacher. Okay, so my top also got square. All right. So now you can find your natural frequency. Betul tak? Natural frequency is 36 square root, and from that natural frequency, what else? So 2, which is 6. So you know that natural frequency is 6. So 2 times with damping ratio times with natural frequency equals to 4.2. So from there, you know your damping ratio, 4.2 over 2 times with natural frequency, which is 4.2 over 2 times with 6.
0.35.
0.35. Betul ke? Are you sure? Yes, 0.
Yeah.
Okay. So that's it. Simple example. Okay. All right. So let's move next. Okay. So when we get 0.35 damping ratio, there is something that we can actually analyze. Okay. So in the books, it gives you table, you can look at in the textbook, it gives you table 4 point, in the textbook, it is table, okay, table 4.11, figure 4.11, okay. So the damping ratio here, it gives some meaning actually. It also can, from the damping ratio, you can predict, okay, what is this kind of response that you get, okay. So if the damping ratio is 0, so you know that, okay, the poles is at the imaginary, so this is not good, so you're going to have an oscillatory response, yeah, right. So if your damping ratio is from 0 to 1, okay, you're going to get a plot that is, the poles will be somewhere in the S-plane, but in the, not at the real part. Okay, it is not at the line, but it is somewhere around this region. Okay, so you know that it can be an underdamped system. So if the damping ratio is equals to 1, so you can expect that the poles is actually sharing the same place, the two poles. Okay, so it is critically damped. So you can expect that, you're going to expect that the output response is critically damped. So if the damping ratio is more than 1, okay, you know that the poles, the two poles is located at the real parts of the S-plane. Yeah? So you can expect that the damping ratio is over there. Okay, so what else you can know? From knowing the damping ratio, also from when you know the damping ratio and also the damping ratio and also the natural frequency, using this formula, you are able to find the poles. Okay, the two poles, okay. So pole 1 and pole 2. So this is the formula. So these are the things that you need to know. Okay, because we're going to have a second order sum system, and you are expected to analyze the system. Okay, so far so good. Okay, so let's move to the sum exercise. So find the damping ratio and identify the kind of response expected for the following system. Right. So for example, for A, so you know that again. So we have the general form which is equals to natural frequency squared over S squared plus 2 times with damping ratio times with natural frequency plus with natural frequency squared. Okay, for the case of A, your natural frequencies will be equals to square root of 12. For the case of B, your natural frequency will be equals to square root of 15. And for the case of C, your natural frequency equals to square root of 10. Okay. So for your damping ratio, it will be 8 over 2. Okay, so correct me if I'm wrong. Okay, so for this one, it will be 8 also over 2 and for the damping ratio for this one, it will be 8 over 2 20. Okay, for the first one, what do you get for A?
0.8.
For A? For the damping ratio for A will be
0.20.
A will be more than 1, am I right?
1.15.
Okay, nice. 1.5, right? So B,
1.15.
apa tu? A, for A. Okay, for B,
1.
1. For C,
0.
it is less than 1. I'm just looking at the answer here, but you can calculate.
0.
Yeah.
It's something, so you know that.
0.89.
Okay, thank you. 0.89, right? So you know that, so from this you can analyze, okay, I know that the first system A is 1.15 meters. Okay? So
Over them.
yeah, for the
Over
system
them. Critic.
and for this
Critically them. And that one is under them.
under them. Right? Okay? So in
And
our
them.
engineering, we are usually talking about.
I
Okay.
wouldn't use.
What are, okay, next chapter, when we're talking about the under them section. Okay, so by now, it should be in your head. Bukanlah by now, but then, okay, under them systems, this. Macam I cakap tu, just imagine like a antenna position control system where we change, we want the position, desired position to move from 0 degree to 90 degree, so the antenna will move. So it is impossible to get the antenna to move and give the response like a critically damped system. It's very impossible because why? Because the antenna is the gears, the environment, right? And of course, we don't want the antenna to have the undamped system. Usually, the normal response will be undamped. Okay. Moving on, we need to know, we are focusing on underdamped second order systems, okay? Because later on, we're going to design a controller, how to make these underdamped in such a way that the overall smooth manner and the setting pump is our aim. So prior to that, you need to know what are the specific you need to know for the underdamped second order response. Okay, so again, I redraw it here. The underdamped second order response is, for example, you have a step input here, okay, a step input, and the system will respond to it. For example, an antenna position control system, we want to move the dish from 0 degree to 90 degree. So what happens? The gears, the motors, the the amplifier, and the gears will move the whole dish. So the whole dish is moving, and then try to settle at 90. Okay, so this is example of underdamped system. Okay, excuse me of my drawings here. Okay, so there are 4 specifications that you need to know. Okay, for the performance of underdamped system. The first one is the peak time, which is the time required for the waveform to go from 0.1 of the final value to 0.9 of the final value. For example, here the final value is 90 degrees. So 0.1 0.1 of the final value could be 10 degree, and 0.9 of the final value could be 80 degree, for example. So this is the time for the rise time here, TR here, the time to rise. Okay. Below here, the rise time. Okay. Peak time. The time required to reach the first or maximum peak. So in this case, it is peak time. T E. Yeah. Peak time. Alamak, I have to keep this too low. Okay. Peak time. Okay. Percent overshoot. The amount that the waveform overshoots the steady state of final value at the peak time expressed as a percentage of the steady state value. So you know that this is the steady state that here. Overshoot is here. Okay, percent overshoot. And the settling time is the time required for the transient dam oscillation to reach and stay within 2% of the. So when it has reached here and it is within 2% plus minus, then this is we call the settling time. Okay, so there are 4 things that you need to know for under-damped second order system. So if you're going to carry it along the way until your system design, if you did some, if you have a system, if you build a system. Okay, so again, this one is just to redraw again, it's much nicer than drawing, of course. Okay, so there are the 4 specifications. For example, this is an example of under-damped second order system. Okay, so there are 4 things that you need to observe. The first is the rise time here, my distant drawings. So it is from 0.1 to 0.9. Okay. The second one is the peak time. Okay. The peak time is where it reaches the peak here. We need to know that. Okay. In order for us to design a control system. The peak time. The third is the percent overshoot. Okay. So the percent overshoot we are looking at from here to some final value here, which is there is a formula for percent overshoot. We will discuss it in the next slide. Okay, I'll draw here first, percent overshoot. And the fourth one is the settling. By definition, look at definition now, it is still within 2% of the steady state value, right? So, for example, this one is the final steady state value. Okay, so the 2% is from 1.02 to 0.98. So as long as this one reaches within this one, okay, so it reaches here, so this is the settling time. Okay, follow me? Okay, so again, this one is the formulas to find the peak time. Okay, you are not given a response like this, but you are given a natural frequency here and also a damping ratio. Okay, so what it's trying to say here is if you know for a system, if you know its natural frequency and its damping ratio, you can actually calculate certain parameters. For example, here is TT, the peak time. Okay, and also you can calculate the percent overshoot. For example, here, okay, so next one is the equation of percent overshoot. Okay, so percent overshoot is the C max minus C final over C final. So let's look at where is C max. So percent overshoot is here, C max minus with C final, which is C final here, with C final. Okay, so this is the percent overshoot. This is C over C final. If it is percent, so you have to multiply by 100. Okay. So there is also another formula to help you find percent overshoot. Okay, so in control engineering, you don't have to worry about if the formula is derived. You just use percent overshoot is equal to an exponential minus damping ratio times with 5 over minus damping of it times with 100. Okay, the good news is you don't have to memorize this, but you are expected to know how to use this formula. Yeah. So another part is this one, the third one is, okay, you have a percent overshoot here, you can estimate the damping ratio. You can calculate the damping ratio, which is a ln minus ln percent overshoot over 100 over with square root of 5 squared plus 2 squared. Okay? All right. So that goes the peak time, percent overshoot, and setting time. So how is setting time? So again, system, you know a system and you know the transfer function. For example, okay, plus AX AB plus B squared, for example. So you, from the system, you know what is the natural frequency and the damping ratio. You also able to find the setting time. You can predict the setting time, not find. You can predict the setting time using through this formula. 4 over minus ratio times frequency. So that's what it says here. Also, if you have a damping ratio, also there is another formula here and another formula that you can use. Well, you have lots of formula. It's just right. So this is another one. Is the how do we evaluate the rise time? So the rise time is based on the damping ratio, and the curve here is the what's required for you. So, for example, you have a damping ratio 0.2. Will be this value. Okay. So example, as the damping ratio increases, you can see that the rise time will decrease. Okay. So this is an exercise. Given the transfer function, you have a system that has a transfer function 100 over s squared plus 15s plus 100. Okay, so find the peak time, percent overshoot, setting time, and rise time. So again, so from this, you know that in general, the system is in the form of natural frequency over s squared plus 2 times the damping ratio, natural frequency, s plus natural frequency squared. Okay, natural frequency here. Okay, so what is the damping ratio? Proper damping ratio? Over 2 times with natural frequency. Am I right? So 15 over 2 times with 10. So berapa you dapat damping ratio? What do you get for the damping ratio?
0.75 ma'am.
0.75.
75.
Sorry. 0.75. Okay. So you look. So now you look parameters here. Okay, natural frequency and damping ratio. So you can use the formula to find the peak time. The peak time just now is Pt equals to pi minus natural frequency over 1 minus damping ratio squared. Okay. Pi over natural frequency root of 1 minus damping ratio squared. Alright. 1 minus damping ratio squared. Berapa you dapat?
0.47.
0.47 second. Alright. So percent overshoot. What is the formula for percent overshoot? Okay, which one you use? Which equation you think
Exponent.
is nice to use? It's easy to use. For percent overshoot. Okay, so percent overshoot is our damping ratio just now is 0.75, right? So just put 0.75 here. What do you get? Percent overshoot. 2.88. Okay.
2.84%.
Okay, so setting time. What is the setting time?
Setting time.
Looking at the formula, setting time. 4 over damping ratio times with natural frequency. So what do you get?
0.53.
And so 0.53. And the rise time. What is the rise time? So you know that your damping ratio just now is what is it? 0.75. So somewhere around here, 0.75. So you're going to expect 0.75. Between 126 to 2.46. So it's approximately around 2.3 seconds.
Yeah.
Okay. So when you have all these parameters, you know what? You can expect how the response looks like. Okay, so we can sketch it here. So you know that this is a second order system because of s to the power of 2. And you know that the damping ratio is 0.75. So as long as it is from 0, then you know that it is under that.
Betul.
Okay. So you know that the under dam system will look like this. Okay. So then you can expect that, okay, what is the peak time? The peak time is here. HPP. What is the setting time? The setting time is 52% of the final value. So your setting time now is somewhere here. Okay, TS. And what is your rise time? Your rise time is percent overshoot first. So the percent overshoot is here. Here. Letak sini no here. So here. So this is the percent overshoot. Okay. So what is your rise time? Your rise time is TR here from 0.1 to 0.9. Okay. So your rise time is from here to here. This is your rise time, which is 2.3 seconds. Clear? Okay. So keep on practicing. Okay. So for example, this one is a lift system. Our lift is more advanced. So instead of first order system, our lift is a second order system, for example. Okay. So how we analyze, for example, the lift, it gives you if we don't know this transfer function, for example, we don't know this transfer function, but it gives you an output response like this. Okay, so you can just find the TP, the time it reached the peak, the time it settles the desired value, and also the rest time, and you are able to find the ratio, and you can go until it reached to this. You can estimate the transfer function. That is, so with all these informations, okay, you are actually ready if the question gives you a model and you are ready to estimate the trend of system. So if the question gives you an output response like this, you should be able to estimate what type of system is that and what is the transfer function. Okay? So far so good? All right. Okay, so this one is what is talking here is about the peak time and also setting time. TP is peak time and TS setting time. Okay, so look at the S plane here. Okay, so the TP is pi over natural frequency, the desired, and TS is actually pi over the, okay, so I'm trying to understand this. Okay, so TP is here, which is pi over the natural frequency, okay, the desired frequency actually, okay? Desired natural frequency, and T at the setting time is 4 divided by the real parts of it. So here, okay, so this is from the poles location. So example, if you have the poles here, okay, you can use this formula, okay, to find TP and TS, to expect the TP and TS. So what it's saying here is that from the poles now, you are given the information that you are given is only a poles location. Okay, so you're given here a location of the poles. So from this location, you can also estimate the peak time and also the setting time. So that's what it's saying for this slide. Okay, so far so good. Okay, also now, so this one, explain. So it shows that, for example, you have a pulse here. Another pulse. Okay, for example, you have a pulse here, so it's actually usually it's here, another one here. So, for example, your system 1 has a pulse here. Okay, so this one is GS1. Sorry. Comparing between two systems. So this one is system 1 and your system 2 has a pulse here. So we can compare time and settling time and overshoot through the location of the pulse. Okay. If you see here, the pulse for system 1 is located here. So from here you can get your TS, and also if you map it to the imaginary okay, it has the pulse here, location of the pulse here. You can predict the setting time for system number 2 and also the peak time for system number 2. Okay, so then you can compare. Okay, system number 1 has faster peak time, and faster setting time, but slower peak time. For example, slower peak time. Compared to system number 2, it has faster peak time but slower settling time. Okay, so that's it. Into that, what happens if the pulse? You have 3 kind of systems. Okay, so which has the pulse located, for example, system 1 here, system 2 here, system 3 here. So what you're going to expect the performance of the whole system. Okay, you can expect that number 3, for the system that has pulse at number 3, it will have a faster rise time. You see this? A faster peak time. Okay, if faster peak time is oscillates at, let me see here. Okay, but it gives a steady state, a longer steady state value. Compared to peak number 1, system number 1, it has a it settles faster. So that's how the analysis can be. So for example, we have the pulse number 2. Okay, you have the pulse at one pulse at system number 1 having the pulse here, and system number 2 having the pulse here. So this is what happens, but it's moving. So it's moving to this side, right? So what you can see is that the pulse is actually, it affects the overshoot of the whole system. Okay, so you see that system number 1 has higher overshoot than system number 2. Okay, so another example is if you have the pulse, 3 systems, you compare the 3 systems, but the pulse location is moving diagonal like this. So the output response that we're going to expect is that, okay, it has a same overshoot, but what happens is that system number 3 will have fast. Okay. All right. So given the plot shown, okay, so what it says is that when you have the system, when you have the pulse, we have the information of the pulse, and we're able to plot it in the S-plane, which has the actually find 90% overshoot and number. The peak time is equals to pi over the imaginary part here, d here. So in this case is pi over 7. Then you will get 0.449 seconds, 4.9 seconds. The percentage overshoot using this formula, you will get 26%. Okay, so the settling time using this formula, 4 over the real part, which is here, is D3. So you will get 1.33 seconds. Okay. Now we are moving to the next part. Okay, example, this is the case where we don't know the transfer function, but we are given an output response. We have a system. where this is black box. We don't know what is the transfer function here. But you are given the output response, which is here. Okay, so you know from this output response, what you can see is that you know that the input is a step. Here. Should before it settles the output. Okay, so you will know that okay, this shape of system that you know that it is under step. From this information, so if you are given the, you can find the Cmax, the maximum here, which is here is given 13.82. The C final here is given 11.03, and is given here TS here. The setting time, which is to reach 2% of this, is 2.62 seconds. You can, and you should be able to find the transfer function, which is 0.6. From this information from TS, you should be able to find what you can see. How you need to find the natural frequency. Okay. So you know that TS is equal to 4 over damping ratio times with natural frequency. Okay. So 4 over damping ratio times with natural frequency. And you know that the percent overshoot is equal to, it gives the C max and C final. So it's actually, you can find the percent overshoot. C max minus C final over C final times with 100. Okay. So what formula am I using? This one. Okay. So from this percent overshoot, you can find the from this percent overshoot, when you get it, some information there, so where you can find probably the damping ratio or the natural frequency. Then lastly, you're going to get this one, the transfer function. You can estimate the transfer function. So this one, I want you to try it. So you can have all these slides. I put it in the e-learning, okay, for you to review and try to do this one until you get the final answer here. Okay, all right. That's all for the lecture today. Okay, so I will, whatever things that we are doing here is, I will record it. Okay, so before that, do you have any question?
No, ma'am.
No, ma'am.
Okay, so this overall, I think if you spend one more time to look at all these things, you should be able to grab. Am I right? No question.
Yes, ma'am.
Okay, thank you so much. So, yeah, I'm going